Hello, everyone. Thank you for attending. So in this presentation, I will be talking about how we are using multimodal models in the telecom industry. I work as a Gen AI R&D engineer. I have a background in telecom, but also now my everyday work is to do AI and Gen AI more specifically. So I work in the System Comprehension Lab. It's a new entity that has been created in Ericsson that is focusing on how we can leverage Gen AI. We are using the Gen AI as a utility for simple task or general task, but we are looking also in the research domain how we can leverage this capability for the telecom industry. And here I need to mention that it's quite difficult things that it's challenging because the telecom industry has been developed for a long time as rule-based domain. So in telecom, we are using a lot of math and probability theory to decode signals and send signals. And we have a lot of algorithms that reach theoretical plateau in terms of efficiency. In terms of latency, in terms of data rate, etc. And so since most of AI algorithm has been developed on, let's say, Van Neumann architecture of computing, we have a problem of latency, which make implementing these models have some challenge. So in this presentation, I will have some brief introduction about what is Gen AI. Maybe you have heard some few things here during different sessions, but I will repeat it simply just to recap, to have a recap. Then talk a little bit about the overview of what we call the AI native wireless system in the telecommunication domain, and how we are seeing the multimodal models as an AI native wireless system. And finally, a solution or a concept, proof of concept that we have developed and tested using the multi-agent workflow. So maybe you have seen this drawing before that has AI circle inside of it, machine learning and deep learning. So basically AI is the design, the system that are designed to do the task that require human intelligence. Inside of it, there is a subpart, which is the machine learning. That is the subset that is taking data and learning from these data. Deep learning is also a subset of machine learning that is using a neural network or more deep neural network. But sometimes people might mix to say Gen AI is subset of deep learning. It's not. This is not right. So Gen AI, it's a concept where we might have an architecture based on deep learning or not. Okay, and the LLM itself is also a subset of Gen AI. Maybe right now is the more attractive, people are using it, but it's still there is a lot of generative AI that are not based on language model or even transformer model. So more in deep, this drawing might explain because we need to fix the taxonomy in order to develop a model and be aligned, especially in the research community, about what we are telling, what we call large AI model and large language model or language model in general. So we have what we call large AI model that might be generative or not. For example, AlphaGo is one of the models that are used to play a game. It's large, but it's not generative. We have also in the generative models, we might have large models and we might have small models, okay? And in the large models also, we might have something based on transformer architecture and not. So the transformer, which is an architecture combining an encoder and decoder together, and sometimes it might be only encoder or only decoder, depending on the application that I will mention afterward. So we have a lot of research in the telecom domain for very specific tasks. For example, time series transformers are used to do some channel estimation that are very efficient and very fast, where we don't need to implement it as a language model. And the language model before, in 2015, when series start to become very efficient, it's because of the LSTM architecture, bidirectional LSTM, long-short term memory, but it lacked for this long context and interconnected context. That's where the paper of 2017 of the transformer showed why this architecture might solve this problem, and then the transformer became very famous. And especially that with transformer, we can easily go very up, like increase the dimensionality of the model, okay, without losing the information between different layers. So how we see the phases of building an LLM, because we need to, as a telecom industry or technology maker in the telecom industry, we need to see where we need to have our position, right? We don't need to reinvent the wheel. For example, the first step is to create what we call the foundation model. Foundation model is created by doing the pre-training phase. And this pre-training phase, we need a very large corpus of data, basically, and a lot of training. So here where we create, like, for example, when we talk about Llama 2 or GPT 3.5, these are foundation models, and they are trained on trillion of tokens. So here we can imagine it as we are creating the architecture of a brain and teach him how to talk, okay? And then if I need to create or to replace a telecom engineer, I don't have to create the brain and teach him how to talk and then teach him the telecom industry. I can start from a level where he can understand the language, right? And also with the multimodality, it means that I'll need a foundation model that has been learned about how to see, how to recognize shapes and images, how to generate images, how to understand language, etc. So for that, we can see that big tech company like Google, Meta, Anthropic, Mistral, and OpenAI, and others also, those are building the large language model. They are investing in creating the foundation model, sorry. Foundation might be language or multimodal. And they have a lot of solution out there, and different foundation model are efficient for some task and other for the other task. And then we have the next step is adaptation to task, which is sometimes we call it alignment, training alignment. So here we have the foundation model that if someone interacts with it, might have some answers that are not relevant. Basically, just to say, a language model is a probabilistic model that will predict the next token. It's not a chatbot, right? But it is prompt. When we use ChatGPT, it is aligned and prompt to act as a chatbot. So basically, under the hood, when we are talking with ChatGPT, there is a prompt saying that you are a chat and you have to answer to the following question, etc. And then when we add the question, it will be able to answer the question. So the alignment might be training or prompting. I will talk about that a little bit later. But we have several tasks. For example, create chatbot, question answering, code generation. The code generation right now might be the most efficient part of LLM in the industries. Information extraction, summarization, etc. And then after the adaptation to the task, we have the adaptation to domain. So here the domain specification, for example, in the telecom, we are developing some chatbot or code generation that are related to the LTE specification, 3GPP standards, NTN, non-terrestrial network, sorry, and security bot, etc. Right? So here we can say that for any kind of task, I can also customize this task create agent to a very specific domain. Because more we need a model that is multi-domain, it means the complexity can increase exponentially in terms of the data quality, in terms of how big this model is, okay? So the customization technique, in terms of, we compare the customization technique with the complexity. We have the prompt engineering, which is the easiest part, I would say, in terms of complexity. It is giving order or teach the LLM how to behave linguistically, okay, by saying, follow this step, this template. I want to send you, like, let's say, act as an interviewer. defining the persona, defining the task to do, etc. And so basically here we are using LLM as a service, okay, from companies that are providing this service, for example, OpenAI or Claude. And this is very efficient on some tasks, like, if, for example, if we need to increase the reasoning capability. We have the LLM that has been trained. We need to teach him how to behave. It's similar to tell someone, if you need to decode the Rubik cube, you should follow these steps, right? You teach him how to do these steps. He is intelligent, but he have never used to solve the Rubik cube, but you are teaching him with context. Sometimes we call this in-context learning. We have retrieval augmented generation, the next step, or RAG. Basically, RAG is similar to have someone who is intelligent, but he has some additional books. He knows how to look for the information. We ask him a question, and he can go to look where is the information, read the information to answer. So it's not, he is not doing searching only. He is answering. He is generating an answer, but based on some data that we are providing. Because basically, we still have some secure data, for example, that we don't need to implement it in the model itself to be trained on. And whatever the model is big, it's not infinitely trained on every data that's outside, right? That's why the RAG is important. Here we have some engineering challenges in terms of providing the data in very high quality in order to the LLM be able to find it. And finally, we have the fine-tuning. And this is the most expensive and most complex part, which is taking the LLM and create a training pipeline in order to retrain it with the data, so that this LLM is specified by itself as an architecture to a very specific application. Now moving to the multimodal models. So briefly, what we have seen, LLM are designed essentially for natural language processing, for to understand languages. And so large multimodal model can integrate multiple types of data, text, images, audio, video, etc. And this can be done by one of there were two architectures deployed, but one of them right now took the lead. One is using encoders, a lot of encoders, in order to decode, like translate any kind of modality into text, and then feeding the LLM itself. It's an LLM. Or we have the architecture that is based on the switch transformer, where we showed that the transformer itself is an architecture that can jointly understand multimodality. But we need an encoder at the beginning that is trainable also. And so, for example, GPT-4, Lava, DALI, Clip, those are models that are based on the switch transformer also, and they are multimodal. So what is an AI native wireless system, to see how we are applying this Gen AI capabilities? So what we called AI native wireless system, basically these are the wireless network that are designed and optimized with AI at their core. Okay, so basically the AI is basic for this application. And here we can see that there is an increment path in order to attend the AI native. At the beginning, we have, these are layers in what we call the OSI layer in telecom. So basically, when we need to send any kind of information, we have the application that is talking with an application, but under the hood, there is several layers where the first three layers are physical layer, where we have the physical wave, how it's sent with the radio frequency, etc., decoding. Then we have the MAC layer that is talking at the MAC in order to see what is the power, security, error check, etc. And we have the network layer that we are talking at this IP connecting, going through these routers, etc. Okay, to say how this message will be sent from A to B. And for each layer, we have different kind of algorithms that are implemented. And this shows that the telecom is not a domain, like not one domain that we can teach the LLM everything inside of it. It's a stack of lot of domains, right? That should be jointly working together. And so we moved from having some blocks of algorithms where some component are using AI, for example, channel estimation, where we need to estimate the channel in order to provide, for example, some functionality. Let's say I'm moving from a place to another place, so my connectivity will move from the first antenna to the second antenna, right? So in order to do this, what we call the handover, that I will be connected to the next cell, these cells should always measure the state of my channel or my signal, right? So these should be measured very fast in order to do the handover also fast, to not have a cut in my call or my any application that I'm using over the internet. And so we have developed some AI models to solve some particular algorithm or task. And then the next step is that the whole application of channel estimation is done by an AI that covers everything in the CSI. And eventually, an AI native physical layer is that we have one AI that can do most of the physical layer part. Okay? So then we will have some networks that can autonomously adapt, optimize, and troubleshoot in real time in order to improve efficiency and the user experience. And so basically, if we see the track of the telecom industry, at the 4G we can say that this is the maximum where the interest is to have a mobile broadband experience. We are using our cell phones to the maximum. We have good coverage with good data rate. Basically, we don't need more. The 4G can do everything we need with the internet. That's why the 5G, we said that it's service-oriented, that operators will monetize on proposing some new services. What kind of services? For example, here we have 3 types of services. Enhanced mobile broadband, which is using our cell phone, but right now to upload some videos in 4K. Okay, so this is a service where we need very high data rate. That's why we have MIMO, we have millimeter wave, etc. We have also massive machine type communication, which is the IoT. So now we have a lot of components that are connected to the internet. And so the infrastructures should hold this gigantic amount of connected devices. And we have what we call ultra-reliable low-latency communication. For example, when we have an operation like remote operation, surgery operation, right? This kind of telecommunication should have a very low latency and also ultra-reliable. And in 5G, we are talking about latency that is down to 1 millisecond in terms of sending the order and having the answer back. Or let's say when we have a communication between vehicle-to-vehicle communication, a vehicle that is integrated in a smart city where like we can avoid accident, etc. Okay? And so the characteristic of an AI native wireless system is that it's self-optimized. It can optimize automatically for any purpose or on intent. For example, I can say, I have here like a food game in this place, or I have a manifestation in that place. I need to optimize my infrastructure so that it should answer to this linguistic task in order to implement this infrastructure. And basically what helped that we moved also with our technology from native, telecom native in terms of hardware-based, and then we moved slowly to virtualize and then cloud native. Cloud native, it means all our network functions are in the cloud right now. Router, switch, firewalls, etc. All telecom components right now are containers, okay? So software defined. So right now we can have some data center, some edge computing where we can implement the network functions. And then we are moving toward the AI native. So the challenges here in the AI native wireless system, we have data complexity and heterogeneity. We have a lot of data, and it's complex and it is heterogeneous. We have images, 3D radars, text, etc. And also the impact of that we need to have a lot of data stream at the same time. We have the real-time processing and scalability. So for this low latency communication, we need to have real-time very fast. We have the problem of interference and noise management. These systems will have a lot of noise and interference that should be tackled. And also, since it's exposed to a lot, like a large amount of data, we have the security and the privacy concern, especially when we have the data compliance legislation. For example, you heard about European AI Act, in order to talk about what kind of data the operator can access or the language model can access. So for that, we find out that multimodal model is a good solution to tackle this kind of problems, where we can see that the model in this kind of systems is in a high level, will have a reasoning engine in the middle, which is the generative model, that can take multimodal type of information, these information that are sensing, location, videos, photos, etc. There is pre-processing pipeline and encoders that will translate any kind of modality into what we call easy to understand language. So any kind of language, it's not English language, okay? So it's like the tokens or like numbers that are entering, but they have the same space, I would say. So the photo of an apple have the same direction or vector representation of the word apple as an explanation. The reasoning engine might be an LLM, might be agent or multi-agent. And then this is connected to two things. We have the digital twins that replicate the reality, because when we have some critical application, we cannot just try on the real world application. We need to run it on, especially when we have, for example, online reinforcement learning application, we cannot run it directly where the user can have some big problem or the operators will face like a cut in their services. We need to implement it first in digital twin to test it and having feedback in order to learn. And this is connected to some SDKs, APIs to provide services, or to the RAN controller, this RAN controller that can deploy the architecture itself that we need. So this is, I will move a little bit fast because of the time, but I would say this is what I mentioned in the figure. So the reasoning engine is the foundation model, or it might be some big models or some large models. And for example, Apple Intelligence have presented an architecture of their LLM-based intelligence, where they have local LLM on device and an LLM on the edge cloud. So we have also this visibility for the LLM. And also we will implement some reasoning capability, either with RAG fine-tuning or prompt engineering that we cited in the other slide. And so the knowledge augmentation, this is how we provide this LLM with information. For example, we have standardization, 3GPP standardization. We have some books about how to do telecom stuff, and we have the sensing data. And we have the action capability that we talk about, APIs, SDKs, or connect to RAN controller to implement these, the architecture. What we are proposing here, like as an example, is a multi-agentic workflow that we can see in order to develop, like to provide a network configuration. It might be one of 3 stages. That's why we moved into multi-agent workflow, or we selected the multi-agent. We have the simplistic design where we ask the LLM and it gives us the output, and we can check the output. We have hierarchical design where we are using multiple LLM to move from different layers. Like the first one will give a high layer configuration, and then the second one will decompose each high layer to simpler layer, etc. And we have the automated design where we have one that generate and the other one that verify. Okay? So we have a feedback that will avoid a lot of human intervention. So this is a proof of concept that we developed in order to create a network function orchestrator. We have 3 main components, 3 agents. We have the semantic router that is here. This is a small model. It's BERT, and it's an encoder only, because it's used for classification. So basically, the user will give an intent saying, let's say, I need to optimize my network in Belgrade, this place, because I have a foot, I need to increase the data rate, for example, or the user experience. This will go to the semantic router that will define, it would say, okay, this request in this domain. It will classify the domain. Since it is a classification, we know that encoder-only architecture are very useful for this kind of application. So this has been fine-tuned on a data set. It was not big. And also the next one is the intent translator. This one will take the intent and will derive a plan. It will create a plan, strategic plan. This agent is connected to a vector database. So we have RAG implemented here, where this vector database have the 3GPP specification. It will go to look in the 3GPP specification to verify what I can do, at what frequency I should operate, etc., what are the standards, to create strategic plan. And then we have, finally, the resolver. The resolver will take this strategic plan, and it will generate what is the function architecture. Briefly here, we implemented some prompt engineering also algorithm. Like, for example, we have React, reasoning, and action. So this algorithm will take an order, will do reasoning, will do action, and will do observation to have a feedback to see like if I'm good or not. So it's kind of chain of thought. So the chain of thought is a prompt engineering where we can tell the LLM to decompose any request into intermediate step. And reasoning and action is chain of thought plus doing the action and have an observation to check if it is good or not. So this is an example of the intent translator. So the request gave a user request, and then it translated this request into, it checked in the 3GPP standardization also, about the specs to give a thought, okay? And then finally, it generates a strategic plan, first, second, third, so there is 3 steps. And after the intent translator, we have the resolver that took this strategic plan to make an implementation. So he did thought, action, where he deployed basically this function. So this resolver is connected to a bunch of functions, Python functions that are implemented, and these Python functions are connected to the network function and the digital twin. And finally, like when he did all this analysis, he will get out with the invoke tool. For example, optimize massive MIMO scheduling, then implement beamforming technique for 5G, then adjust the beam direction dynamically. So I moved very fast just to keep some time for questions. Sorry for that, but if you have any question, please. Yes.
Hello, thank you for presentation. I have one question regarding latency. Because you said that your system is depending on low latency. How did you achieve that with LLMs? Because they're never responding immediately. They have lots of latency. And another question, maybe if you have time, if not, why using LangChain and not prompt flow?
Yes. So basically, LangChain, just start with the second question. LangChain is for fast development because we have seen that open source community is moving very fast with AI, etc. So we can very fast deploy some new algorithm outside on LangChain, but basically we are developing the solutions on Bedrock AWS. That's what we are using actually. So everything here will be translated to Bedrock, to build it on Bedrock because for the stability part. But usually we choose LangChain because it's on the edge of what's happening outside. And the first question is about latency. So latency is not resolved here. What we are starting to do is that the LLM lack a lot about understanding telecom standards and reason as a telecom engineer. So we need to solve the reasoning part, and afterward, moving into solving the latency part. For that, we have one vision, that is, we have the model distillation or quantization so that we can reduce the model size to have faster inference, or to deploy a hybrid architecture where we have big model deployed at the edge and smaller model, big model deployed at the center and smaller model that are more specialized at the edge. With that, also there is a lot of other parameters about what is the accelerator that we need to use, what kind of algorithm we can do to enhance the throughput. But yes, it is a challenge that is not resolved from the beginning. It needs multiple parts to be together implemented.
Thank you.
Welcome.
Maybe another question, if there is another one for you, sir.
So the 3GPP standards layer on each other in sometimes quite complicated ways. How did you deal with that with the RAG approach? Like, are you simply trying to, in your search, collect every reference to that specification building over time? Or is that taken care of in pre-processing where you're trying to collate like the current standards?
Yeah, so this was one of the main challenges in our pre-processing pipeline. We have been working a lot on it, and we realized two things. First, the representation of the document itself. So we cannot just take we started with just putting the document in a vector database, and we have a lot of hallucination. That's what you have mentioned. But next, we moved to first do rule-based processing in terms of like using Markdown with some comments on it, add a lot of text that describe, to push also the vector representation toward when to choose this chunk. And second, the second one that gives some good answer is to use graph representation. So with the graph, you can have more punctual, let's say, or higher resolution about finding the chunk that you need. But for sure, this to work well, we need to do, in addition, the prompt translation. So the prompt that is coming should not ask a wide question about, like, for example, what is the frequency of doing the IoT? No, it should be what is the frequency of the IoT such that I'm implementing in 4G at this, using, I don't know, this release of 3GPP, etc. So it needs to specify all of that in order to find the right chunk. But this is the challenge, as you mentioned.
Sorry, if I can get in a second question there. The example you showed was triggered by a user. So user put input, and then that triggered the response. Have you looked at triggering that based on alarms or anomalies detected in the network so that KPI dips would automatically trigger this whole process?
Yeah, this is another work that has been done with another team in Sweden. It has been published, that is following the protocol in order to detect anomaly alarm. But basically the challenge of the task here is that the LLM should understand the protocol as a whole to find anomaly. What we are trying to do is more the generation part, that we have an intent, we need him to reason. But at the end, in an AI native, we should combine everything. But this was a separate work, as you mentioned.
Thank you very much for your questions, and thank you very much for the presentation. This is a small token of gratitude from the organizers.
Thank you very much.
Thank you.